Good afternoon. My name is Yoon Byung-chae. Today my presentation is about robust self-supervised learning and out-of-distribution detection. Let's begin my presentation. My presentation today will cover the following content. I will talk about self-supervised learning, robust to adversarial attack, and robust out-of-distribution detection. Robust to adversarial perturbation will be also introduced. We will look at the papers related with adversarial learning with unlabeled data. I want to know more about out-of-distribution detection in self-supervised learning using robustness of a model. First paper is about a simple framework for contrastive learning of visual representation, as known as SIMCR. A stochastic data augmentation module that randomly transforms any given image example generates two correlated variations of the same example which are considered as a positive pair. Two separate data augmentation operators, T and T prime, are sampled from the same family of augmentation. A neural network-based encoder, F, that extracts representation vectors from augmented data example. In this paper, ResNet is chosen for function F to obtain H. Projection head G that maps representations to the space where contrastive loss is applied. MLP with one hidden layer is used for function G to obtain Z. A base encoder network F and projection head G are trained to maximize agreement using a contrastive loss. After training is completed, we throw away the projection head G and use encoder F and representation H for downstream tasks. You can see illustrations of the data augmentation operators. Each augmentation can transform data stochastically with some internal parameters. For example, rotation and noise level. This loss is termed the normalized temperature scaled cross entropy loss. Function sim is cosine similarity between two representation vectors, and tau is the temperature parameter which can help the model learn from hard negatives. You can see term in the green box. It is indicator function evaluating to 1 if and only if k is not equal to I. So the denominator is the sum of similarity of negative samples, and the numerator is similarity of the positive sample. As a result, similarity of the positive samples becomes bigger, and similarity of the negative samples becomes smaller. And this loss function can show even express how different the negative samples are. To make the comparisons fair, the same L2 normalization is used for all loss functions, and the hyperparameter is tuned. Table 4 shows the results. While semi-hard negative mining helps, the best result is still much worse than our default, the normalized temperature scaled cross entropy loss. The vulnerability of neural networks to imperceptibly small perturbations has been a crucial challenge. Various studies have been proposed to ensure the robustness of the trained networks against adversarial attacks. There is usually features the model is unreasonably sensitive to. We can change this feature to create an adversarial example It looks like a pig to humans, but the model says it's a rhino. Human perception and cognition are robust to a vast range of perturbations in the real world. Yet adversarial examples show that deep networks are currently far from achieving the same level of robustness. Given such a data set and a model, adversarial attacks aim towards finding the worst case examples nearby by searching for the perturbation, which maximizes the loss within a certain radius from the sample. Recent works have shown that self-supervised learning with unlabeled data could help the model to obtain more robust representations. Using self-supervision signal in terms of perceptual loss also shows effective results in denoising the adversarial perturbation as purifier network. However, this paper aims to obtain comparable robust accuracy over state-of-the-art supervised adversarial learning methods with efficiency. While some recent works propose semi-supervised adversarial learning methods that utilize unlabeled data, they still require class labels. The most popular approach to achieve adversarial robustness is adversarial learning, which trains the model with samples perturbed to maximize the loss on the target model. In this paper, we propose a novel adversarial attack for unlabeled data, which makes the model confuse the instance level identities of the perturbed data samples. ROCL, a self-supervised contrastive learning framework, is presented to adversarially train a robust neural network without labeled data, which aims to maximize the similarity between a random augmentation of data sample and each instance-wise adversarial perturbation. Random augmentation is identical with Shim-Sierras. Function B is L infinite number around X with radius epsilon, and pi is the projection function for number. The alpha is the step size of the attacks, and sign returns the sign of the vector. In instance-wise attacks iteration, adversarial example that maximize the contrastive loss is generated, and model's weight is updated for minimizing the total loss. During adversarial training, we maximize the similarity between two differently transformed examples, Tx and T'X, and their adversarial perturbation, Txadv. After the model is fully trained to obtain robustness, then we evaluate the model on the target classification test by using linear model instead of projector. Here we could either train the linear classifier only on clean examples or adversarially train it with class adversarial examples. Existing self-supervised learning models leverage linear evaluation, which runs a linear layer on top of the fixed embedding layer with clean examples. To properly evaluate the robustness against a specific type of attack, the authors propose a new evaluation protocol, which we refer to as Robust Linear Evaluation, RLE. It could be also used as an efficient means of obtaining an adversarially robust network using network pre-trained using self-supervised learning. The unit of figures in this table is accuracy. Our models are trained with L infinite. Thus, the L infinite is the seen adversarial attack, and L2 and L1 attacks are unseen. We first compare ROCL against SimCLR, which is vanilla, self-supervised contrastive learning model. The result shows that SimCLR is extremely vulnerable to adversarial attacks. However, ROCL achieves high robust accuracy, 40.27, against the target L infinite attack. This is an impressive result which demonstrates that it is possible to train adversarially robust models without any labeled data. Moreover, ROCL plus RLE outperform supervised adversarial training and obtains comparable performance to TRACE. My assumption is if robust self-supervised pre-trained model is trained well, the model will map data from OD with iterative adversarial perturbation to noise embedding. But if data from in-distribution test, output will be stable. If we utilize the model's robustness, we may accomplish OD detection from unlabeled data. Thank you for listening my presentation, and if you have any question, please ask me.